so unsteady state. Let's start with some examples. One is pharmacokinetics. If you take a drug, if you take a pill, that drug has some kind of kinetic lifetime in your body, how long it circulates and how long it activates. So a lot of times we want to look at what's the concentration of the drug in the bloodstream. And ideally have a certain concentration you want to hit that's is effective and low enough to be safe and have fewer side effects, and you want a nice steady concentration of the drug in your bloodstream. But is that what happens when you take a pill in your mouth? Do you get instantly that concentration and hold it there? So if you have I have this cold that's going around, I've got a headache, and then I take my Tylenol, and it takes a little while before it kicks in, then I'm good for a while, and then it wears off, right? So if we plot concentration of drug in the bloodstream over time, well, let's see. I could actually draw a little bit of a process diagram. I could put, I'm actually going to take that drug and put it in my stomach, or the gastrointestinal tract, and somehow that drug then is going to feed out into the bloodstream. Eventually it's going to go to my kidneys and the bladder and out, right? What I really want to know is the concentration in the blood. So I can think of this as a process. I can make a block diagram, and I really want to know in here what's the concentration of drug. Okay, so we can model this with some unsteady state reactions, some unsteady state material balances. So let's see, if it takes some time to, if time 0 is when I take the pill, if it takes a little bit of time for it to get into my bloodstream, that concentration in the bloodstream is going to take some time to come up. And then there's going to take some time for the kidneys to sequester it, degrade it, and excrete it. So, and you'll get this exponential decay. Does that make sense? Just intuitively? We might then want to ask questions like, how long does it take to get to the maximum time? We might ask, what's the concentration that it gets to that's maximum? We might want to know the total area under this curve. Might tell us something about the total action of the drug. We also might know, maybe there's a concentration where it starts being effective with my headache. And I might want to know what time does it take to get to that concentration, and at what time does it drop below that concentration. So all those I could answer if I could set up a material balance of the drug flowing in and out. Yeah, and then what happens once the drug starts to wear off, my headache starts to come back, then I take another pill, and depending on where I do that, I've already got some drug in my system. So let's say maybe at 6 hours for Tylenol, I take another drug, and from here the concentration is going to go up again. It might go higher this time because I'm starting from a higher concentration, and then come back down. 6 hours later, I will do the same thing. So that's one example of an unsteady state system. What's the key term I'm going to have to look at in my material balance to get unsteady state? Like one we always cross off when we have steady state? Accumulation, right? So the accumulation is going to be key here. Accumulation, which, yeah. So we'll get to the math momentarily. Let's see, a second example would be the catalytic converter in your car. So your tailpipe got this catalytic converter, and into that goes hydrocarbon that didn't get burned up in your car engine, carbon monoxide from incomplete combustion, and then some nitrous oxide, some nitrates that also weren't completely left over in the fuel. The catalysts on these are key: aluminum oxides, cerium oxides, platinum, palladium, and/or rhodium. These are fairly expensive parts of the car. That's why the auto industry resisted them for a long time. But eventually what we want to come out is CO2, H2O, and just plain old nitrogen. So actually we've done a few problems with automobile engines, and we looked at a continuous feed of gasoline and a continuous combustion of that. So we can think of a gasoline engine of a continuous process, but I bring this up in the unsteady state because 60 to 80% of hydrocarbon emissions are produced during startup. So when you start your car, why is that true? Why is this just? Why do we get all the emissions at the beginning? You know? The engine's cold, right? So the key is that we need this to heat up. These reactions is just like the Haber process that runs at a high temperature. We need this to warm up before the reactions are really working well. When it's cold, reactions don't go out, all these hydrocarbons just go out the tailpipe. Okay, so we may want to look at an unsteady state material balance of stuff going in and how much is reacting and how much is coming out. And this is one that we're going to have to couple to the energetics, because we're going to have to look at how long does it take to heat up, or we'll have to know something about temperatures so we know the rates. We certainly need to look at how this changes during time. Okay, so let's go to a general material balance, and let's do the math. So the general material balance, talked about much input minus output plus generation minus consumption equals accumulation. All right, so that's our general balance that we start from. Where does this come from? This comes from conservation of mass, the first zeroth law of thermodynamics, conservation of mass. If we have some system, I don't know, the system can be any random shape, and we have some inputs and we have some outputs, and we've got stuff in the system. If I want to balance the mass in the system, mass is conserved, so the mass in the system is going to be mass that comes in and mass that comes out. How about generation and consumption? Can I generate or consume mass? So when can I generate mass or consume mass?
Nuclear reaction.
A nuclear reaction, right? So E equals mc squared, so if we assume your E equals mc squared, where I convert energy into mass, if we ignored that, so if you're going to join a nuclear plant and be a nuclear engineer, you're going to have to bring this back in and couple your material and energy balances, but most of the time in chemical engineering we won't do that. So mass is conserved, meaning total mass is not generated or consumed. Let's see, so total mass, dm dt, our total mass accumulated in the system, dm dt. It's going to be mass going in, I'm going to call that m in dot, minus mass out, m out dot. Let's see, so the dot means this is a flow rate. So the units are mass per time. And then over here for accumulation, these units are also system mass. I find that a little bit clunky to write that all the time, so I'm just going to use an M for the total mass. Let's say we're given M in dot is 1 kilogram per hour, and M out dot is 2 kilograms per hour. Let's say we're asked to find dm dt and m of t. So I'm told that flowing into the system is 1 kilogram every hour. Flowing out of the system, 2 kilograms every hour. Find dm dt, that's the accumulation, or how is mass changing with time in the system. And then find the mass in the system with time. Okay, so we just subtracted 1 from 2. How about some units? Kilograms per hour. So that means my system is losing a kilogram every hour. And the mass minus t. So if I plot mass in the system versus time, minus t then will look like this. All right, so we're gonna integrate this. And when we integrate this, we have to integrate it from some initial time to some final time. We're going to get minus t from some initial time to some final time. And we need a boundary condition. We need to know, say, where things are going to start for some constant integration. So we can have some constant minus t. So probably we'd start from some constant and then decrease. That constant might be the initial mass. I might call it M0. HIV therapy. A long-term HIV patient has 1,000 infected T cells. The T cells are the immune cells that get infected. These cells die off naturally at a rate of 10 cells per day and are regularly generated at the same rate. A new drug is introduced that reduces the rate of generation. I don't know what happened to my subscripts. To Rgen, that should be our rate of generation. 10e to the minus 5t, where t is in days and the rate is in cells per day. And the question is, find the number of T cells in the patient as a function of time. Great, so what do you have for accumulation then?
DHDT.
DHDT?
Uh-huh.
What does H mean?
Number of cells of HIV.
Number of cells
Of HIV.
of HIV, great. Infected HIV T cells, okay. Generation?
10e to the negative 5t.
Okay, so let's do Gen equals 10e to the minus 5t. Call that Hgen dot. 10e to the minus 5t. And consumption?
Minus 10.
Minus 10. So I have H consumed dot equals 10. And these are both in units of
Cells per day.
cells per day, which means this DHDT is also in the units of cells per day. Great. Anything else? At t equals 0,
DHDT is 1,000.
DHDT is
Oh yeah,
H is 1,000.
Yeah.
1,000 what? Cells. Yeah, so what do we call that in differential equations? Initial condition. Okay. Yeah, so I think there's been some confusion. Some people want to put the 1,000 accumulated, because that's like the total stuff. So that's part of it. We'll get more practice with that and get that separated out. 1,000 is the initial condition. It's not the accumulated. Where we start from, it doesn't even come in the material balance at all. Okay. Great. Can we solve this? DHDT, how do I solve this? Equals 10 to the minus 5t minus 10. DH equals T, I can integrate from H initial to H final. T initial, I'll just make the time 0 to some final time. Integrate dH, I'll just get H minus H naught, or let's kind of call it delta H equals, let's see, integral of 10 e to the minus 5t is
minus 2 e to the minus 5t.
2 e to the minus 5t, because I took the minus 5 down, I need a minus there. Integral of 10 minus 10t, integrate that from 0 up to some final t. I have to plug those in. Let's see, so minus 2e to the minus 5t minus 2e to the minus 5 times 0 minus 10 to minus 0. So plugging in t at 0, I'm being a little sloppy because I'm using t for the final and t for the integration variables. You might put tf there if that makes it more clear. All right, what's e to the 0?
1.
It's 1. Two minus signs there. So I'm going to get 2 times 1 minus e to the minus 5t minus 10t equals the change in h. Am I done? What else? Real close.
You have to solve, in my case, I have to solve for the constant of integration to get a particular solution.
Solve for the constant integration.
Yeah, because I didn't use a definite integral. for
Okay, so if you okay, so I put h minus h naught on the left.
Yeah, I didn't use
You
the
can also
definite-
just put plus c and then solve for it. So I have no h naught, so I'm going to put in h naught is, this is 1,000, so this is actually h minus 1,000. So I'm just add that on the other side. So h equals 1,000 plus 2, 1 minus e to the minus 5t minus 10t. Time versus cells. Okay, start at 1,000, right? Because at time equals 0, this is 1. This is 1, that goes away, that goes away. So I start at 1,000. And I think the curve's going to look like that. Eventually the slope will be minus 10. So if I look at the thing I could do is I can plot h gen, should I just erased, is 10 to the minus 5t. So h gen starts pretty high and then decays down to 0. This is for time. And h consumed is h consumed is steady at 10. So it'll start flat, and then as I get more and more being consumed, I'm going to consume more. I want to go back to the mass stuff. So mass, we have mass in and mass out equals accumulation. That works for the total mass in the system. Total mass I cannot generate or destroy. However, I can also do balances on individual components. So back to the theory. So total mass is conserved. Components, see how much carbon dioxide is in this system. Oops, I erased my system. How much carbon dioxide is in the system the total mass of carbon dioxide might change, right? How can I change the total mass of a compound?
With a chemical reaction.
With a chemical reaction, right? So, for example, let's do the favorite chemical engineer's reaction. A goes to 2B. Theorists, I love this reaction. I don't know if you know any specifics. Let's say I have a reaction where A goes to 2B. I have a reactor. I have some mass of A in the reactor, some mass of B in reactor. I have a mass of A in stream 1 flowing in, and I put a dot to indicate that that's a flow rate. There's no dot in the system, that's not a flow rate. This is kilograms per time. So I might have a flow rate in MA1, and I might have a flow rate in MB1. And then in stream 2 coming out, you can have MA2 and MB2. That's my flow rates coming out. So total mass going in equals the total mass going out at steady state, where accumulation is the in minus the out. But for A can get consumed by this reaction. Okay, so accumulation of A equals the input of A minus the output of A plus the generation of A minus the consumption of A. So how am I going to write this? The accumulation of A, I'm going to write as dMA dt, the change of mass in the system, equals the flow rate of A in, so there's MA1 dot, minus the flow out, MA2 dot, and then this generation and consumption. What do we do for this in the past? In the past, we just said A gen and A consumed. What I want to do is call this, the two of these together, some reaction rate of a capital RA dot, the net generation or consumption of A. Okay. This is the net generation or consumption of A. If I do that, then I can also say dME dt equals B1 dot minus B2 dot plus RB dot. If A is going to 2B, and I consume a few kilos of A, how many kilos of B do I make?
Twice as much.
Say let's say I consume 5 kilos of A, how many kilos of B am I going to make? 5 or 10? How many say 5? How many say 10? How many have a different answer? What do you think, Troy?
It should be based on moles, not mass.
It should be based on moles, not mass. So moles, we're going to get twice as many moles out. How much mass will we get out, though?
It's negligible.
So mass is conserved, right? Can't generate, we're not going to consume or generate mass. So if I react away so many kilos here, I'll make the same kilos here. So it's 5 kilos there, 5 kilos there. So RA, in this case, when there's just A and B, RA and AB, RB, are going to be the same but opposite sign. Let's see. But you're right, we know things about moles. So from stoichiometry, we know generation of B is 2 times the generation of, 2 times the consumption of A, right? In what units? Moles or something. Moles per time. Okay, so what we're going to do is, in the past we just said A consumed and B consumed. What we're going to do now is use a variable for this and have one variable to collapse this. I'm going to say little RA dot is mu A times C, which is this squiggly little Greek character. And R dot B is mu B times C dot. These are both in moles per time. And let's see, see, what's new A and new B in this system? What's new A? What's new again? Stoichiometric coefficient. What's new for A? -1, new for B. Okay, so R dot A is going to be -1 times C dot. RB is going to be 2 times C dot. So if C dot is 1 mole per second, the change in moles of A would be -1 mole of A. The change in moles of B would be generated as 2 moles of B. Right, does that make sense? Okay, these are moles. We were talking about mass balances, so what I really want is capital RA dot. I want the mass of A. How do I change moles of A into mass of A? I need the molecular weight of A, then I'm going to multiply this by mu A, C I dot. And now these units are mass per time. Our B dot is going to be the mass, molecular mass of B times mu of B times psi dot. It's also mass per time. So, all right. What else? Remember degrees of freedom. Murphy, if we have system, how many system variables do you have under Murphy's degrees of freedom rules? Murphy, we count degrees of freedom. So we have the number of stream variables, and then she says we add system variables, we get 1 for every reaction. That's the variable. We now have a name for that variable, it's called C. For every reaction, we're going to have C. So we'll number these. When we have multiple reactions, we have C1, C2, C3. That's the degree of freedom that we're solving for. So we're solving for ins and outs in the reaction, and then as far as generation and consumption goes, it comes right out of that variable, so you don't need extra variables for that. So remember how it was weird that we had A gen and B consumed, and when I told you forget all that, just count 1 for the reaction. Now it will make a little more sense as we have that variable. So this variable is called extent of reaction. And it's how many moles, or in a batch system, how many moles have reacted, or in a continuous system, how many moles per time have been reacted.
C is called, the Greek letter is called extent.
That Greek letter, that's C, that's the extent of reaction. So the extent of reaction, this reaction could be 1 mole per time being reacted. Here we did mass balances here, total mass, component and component mass, A and B. Now I want to do mole balances. Seems like I'm just throwing out equations, but what we're doing is deriving these, so the total mass balance comes right out of thermodynamics. You can't create or destroy mass. This comes out of that same equation. We get to this, but now we've just separated out the components. We've just done some bookkeeping. Now I'm going to take these equations and change them to moles. I want to take the equation for A and turn it into moles. So component mole balances. If I take the molecular mass, and I take the whole equation and I divide it by the molecular mass of A. Change of mass of A per time divided by the molecular mass will give me the change of moles of A per time. So Na equals M A over molecular weight of A. That's a small m and a big M. Mass flow rate of A going in, Ma1 dot. If I divide that by the molecular weight of A, I'll get Na1 dot moles of A going in. Same thing for moles of A going out. So I'm deriving the component mole balance change of moles per time inside the system is the mole rate flowing in minus the mole rate flowing out minus or plus this RA divided by the mass of A. We're going to get, these are with dots, lowercase RA, which I defined over here. RA, capital RA is MA mu A C, and RA is just mu A times C dot. So minus mu A C dot. Okay, so that's still really actually just a mass balance coming from the first law of thermodynamics, plus the bookkeeping separating A and B, but now we've got it all in moles. We can do the same thing with B. D and BT is the in, and B1 dot minus the out, and B2 dot, that should be a plus nu B psi dot. It's plus, and then the nu's take care for us whether the sign is negative or positive. So that A will be consumed because nu A is negative. And again, I've got one variable for the reaction that comes up in both our material balances, so that's kind of nice. Then I can sum these. dNA plus NB dt equals NA1 dot plus NB1 dot minus NB2 dot minus NB and A2 dot minus NB2 dot plus nu A psi dot plus nu B psi dot. NA plus NB, the number of moles of A plus the number of moles of B. I could also just call the total moles in the system. N equals NA plus NB. So I can call this dN dt. NA dot, N dot A1 and N dot A2 is really just the sum of these two. Sorry, NA1 and NB1. The sum of those is really just the flow rate of all of stream 1. NA1 dot plus NB1 dot is the flow rate N1 dot. So I'm going to call this M1 dot or N1 dot, depending on if you mass or moles. So I take these two together, and N1 dot. Same thing for the outputs, minus N2 dot. So now the change of moles in the system is the mole rate, flow rate coming in stream 1 minus the molar flow rate coming out in stream 2 plus mu A plus mu B psi dot. So the total moles in the system moles in minus moles out, plus we could have moles generated or consumed. In this case, if we go from 1 mole to 2 moles, we might, every time we have a reaction go, for every xi dot moles of reaction, generate stuff.
In the winter